So, welcome to your first online lesson of the unit of work of bonding and properties from your chemistry course. So, if you've got a booklet in front of you, you will need to turn to page 4, where you'll see the first lesson is on covalent bonding. Now, at the top, you'll see written some of the key points that we'll be trying to go through and learn during this lesson. So if you've done that, have a little look down at the knowledge check questions. Now you'll see 4 on this page, 4 on the next page, and what I'd like you to do now is pause the video, have a look at those 8 questions, see how many of them you can answer, either using your own independent resources or just from your own knowledge, based on what you know about the structure of the atom and also aspects you know about the periodic table. So pause the video now and have a go. Right. Now that you've paused the video, let's go through the answers nice and quickly. So, first one, name the subatomic particle that orbits the nucleus. Hopefully you will have recalled that that is the electron. Name the subatomic particle that has a negative charge. Hopefully you'll also have recalled that that is the electron as well. It has a negative electrical charge as part of it. Give the overall charge of an atom. The answer you should have found is neutral, which in simpler speak means it has no charge. The positive and negative charge of the atom cancels each other out. State the feature that all elements in group 7 have in common. They all have 7 electrons in their outer shell, or 7 valence electrons. And if you remember for shorthand, we just write E minus to show that we mean an electron. Right, and then on to the next page, you will see the 8 questions at the top. Write the electronic structure of the first 3 shells of an atom. So what that means is how many electrons are in each shell. So for the first 3 shells, you should remember that the pattern is 2 electrons, then 8, then 8. Name the 2 main groups that elements are divided into. Now you find all elements on the periodic table, and the periodic table is split into 2 groups of metals and non-metals. Give the overall charge of the nucleus. Now the nucleus is made up of 2 subatomic particles, protons and neutrons. Protons are positive. Neutrons are neutral. They have no charge. So overall, the charge of the nucleus, if they're only made of protons and neutrons, is positive. Name the group in the periodic table that are unreactive. So if you remember, when we're talking about groups in the periodic table, we're talking about columns. And go from 1 to 8, or sometimes 1 to 7 and then 0 on the end, depending on the periodic table you're looking at. And the name of the group that is unreactive is the noble gases, which is group 8, or sometimes 0, you might see written in the periodic table. Right, moving on. So what is this lesson going to be teaching you about? Now, 2 main points of this lesson are to try and describe and explain why molecules bond covalently, and see if we can start to draw covalent bonding in simple molecules. So, if we're just going to break down some of the information that's given to you in this text, and then we're going to have a look at how we go about practicing drawing covalent bonding. So, if we read through the text here, I'm just going to read through it with you and then just highlight and annotate and add in some important points about this text. So, first sentence on line 1 says, apart from the noble gases in group 0, all elements have atoms with incomplete outer shells, highest energy level, in brackets. So, the defining feature of noble gases. If all elements have atoms with incomplete outer shells, noble gases, their outer shells are complete. or full. Which means they contain 8 electrons in their outer shell. Okay? Now, these are obviously valence electrons. And if you remember from looking at atoms, also chemical reactions, atoms are always trying to fill their outer shells. So they try to fill their outer shells by reacting and bonding. Which means that if these noble gases already have a complete full outer shell, the defining attribute of them, that was a bit of a rubbish arrow drawn, is that they are unreactive. You might be able to remember some of the noble gases in terms of examples. These are things like argon, neon, a couple of examples. Right, the unfinished shells of the non-metals require extra electrons to become full. Only then will atoms become stable and unreactive. So the unfinished shells of the non-metals require extra electrons to become full. So non-metals, we're talking about group 5 and upwards in the periodic table. And what they do is they obviously gain electrons. To get a full outer shell. And then in the absence of any metal atoms and in the presence of other non-metal atoms, they will only be able to complete their outer shells by sharing electrons with each other. We see this as a chemical reaction. So, 2 key attributes here about covalent bonding. It's between non-metal atoms. So, non-metals covalently bond. And the other key attribute of a covalent bond is that they share electrons, or they share valence electrons to get a full outer shell. So that's our first key attribute of a covalent bond. It's between non-metals and they share valence electrons to get a full outer shell. Now, they share these electrons, and what happens is they can become chemically bonded, so a chemical reaction occurs. And you have a new substance formed. So it's more than just a physical change. Where, for example, if you boil water, it becomes steam. The molecules of water themselves, the H2O, aren't chemically changing, they're just coming further apart and moving quicker. Whereas in a covalent bond, different elements are combining and joining together to form a new substance. Therefore, you've got a chemical change, not just a physical change. Right. Go and take a drink. And if we move on to the next section, forming covalent bonds. So now we know what a covalent bond is and what it's between. We need to know a little bit more about the attributes of it. So let's read through this first paragraph. Covalent bonds are strong. A covalent bond only occurs between 2 non-metal atoms. A single covalent bond is one pair of electrons are shared, one from each atom. A double covalent bond is when 2 pairs of electrons are shared and is much stronger than a single bond. Similarly, a triple bond is when 3 pairs of electrons is shared and is stronger than a single and a double. The type of covalent bond depends on how many electrons are needed to complete the outer shell of each atom. Right. Let's think about this and just break down a couple of key points. So, if we look at the fact that when you are sharing pairs of electrons, you get a specific type of bond. So a single bond is when one pair of electrons is shared. Double bond is when two pairs of electrons are shared. And a triple bond is when three pairs of electrons are shared. Now, a double bond is much stronger than a single bond. Now, if you have a chemical bond that is stronger than another bond, what that is telling you is that you need more energy to break the bond. So if you wanted to break the bond between two atoms that were covalently bonded and they had a double covalent bond, you'd need to heat it more, so the atoms gained more energy, and that transferred to kinetic energy, and the atoms vibrated more and therefore could break apart more easily. The same applies as a triple bond as well. Now, coming back to that point from a couple of minutes ago, a covalent bond only occurs between two non-metal atoms. So if you think about it on a very simple level, one of the most simplest of non-metal atoms that we know about is hydrogen, which on the periodic table you'll see has got atomic number of 1. Now what that's telling you is it's got one electron in its outer shell. So if we draw an electron shell diagram of hydrogen, we've just got one shell. Now, if we're bonding hydrogen together, we end up with H2. So we draw two atoms like so. We have a little overlap in the middle, and this overlap shows where electrons are shared. Now, I've not drawn that very well, but what you should see is a dot and a cross here to represent the shared pair of electrons between the two hydrogen atoms. Now, any electrons in this shell, they both count to filling the outer shell with the other atom. Now, if you remember our electronic structure, the first three shells of an atom, the first shell of every atom needs 2. So if the electron from this hydrogen atom is also counted as this one, then this one now has 1 and 2, so it has a full outer shell, which means it's stable. And then if the electron from this one counts in this one, this then has 1 and 2, which means it has a full outer shell, which is stable. Now, we would use, and I should have drawn it there, but my pen's a bit rubbish here, a dot and a cross to show electrons from each atom. So to show electrons from each atom, we're using a dot and a cross so we can tell which electron comes from which. Now, that's how we represent it. If we had a double covalent bond, we would have 4 electrons in the middle here. If we had a triple, we'd have 6 electrons in the middle here. Okay? So this is the starting point, but we'll look more at these diagrams in a minute. Now, in order to share the electrons, the atoms need to form a bond which locks them together. That there, an example of our bond. Okay? Now, this bond can be broken if enough energy is available from the surroundings to break it. Basically, if it is warm enough. So to break bonds, what do you have to do? You have to heat them, and they gain thermal energy. The atoms gain thermal energy, which means if they've gained thermal energy, that can become kinetic energy. So each atom has more kinetic energy, which means it is moving and vibrating more, which means it is more likely to break apart. Now, the shells appear to overlap. As we've set up here, they overlap. So each atom in the bond appears to have a full outer shell. This is a clever trick for the atoms that they need to perform because their priority is to fill the shell and become stable. And if you remember, if it is atom is stable, it is unreactive. Covalent bond is a consequence of this deal. Now the diagram below shows simplified diagrams of the atoms and the molecules they are bonded to become. So, remember, our crossing over, our overlaps is where our electrons go. So if we look to now turn to the next page to see a couple of examples and go through these examples together. So you should be on to page 6 now. At the top of page 6, you'll see two diagrams like this. Now, compared to the rubbish version that I just drew, this is exactly the same here. As you'll see, the hydrogen atoms, hydrogen is in group 1 of the periodic table, which means it has one valence electron. It has one valence electron. And because it has an atomic number of 1, it means it also has 1 electron in total per atom. Now, because it's got 1 shell, it means it's got to have 2 electrons to get a full outer shell. So what it does, as we've said, is it crosses over, and this overlap, the electrons are shared. Now, if I covered over that hydrogen atom, you'll then see that this one has got 2 electrons that count towards its electronic structure, which means it's got a full shell, which means it's stable. Do the same over here. 1, 2. Again, means it's got a full shell, which means it's stable. Now, if we've got these just 2 electrons that are being shared, what we have is we have a single covalent bond. Whereas if you look here, oxygen itself, just reposition my page, apologies about that, is in group 6. So this means that an oxygen atom has 6 valence electrons. Now, oxygen atoms are much bigger than hydrogen atoms, so also they will have more electrons in shells inside here. But to simplify these diagrams, we don't draw those inner shells, okay? So we've got to bear in mind that we're just thinking about the outside shell. Now, because it's got more shells on the inside, the maximum number of electrons that we can have in the valence electron shell is 8. So if you look here at both these oxygen atoms, we've got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. They can have up to 8. If they have 8, it means they become stable and unreactive, which is what every single atom wants to do. It's almost purpose in life, why they react together. So, if we think about it, we've got 6 valence electrons, 6 valence electrons. It means that both of these atoms, they need to gain 2 electrons to get a full outer shell. So the way in which they do that is they cross over and they covalently bond, and they share 2 pairs of electrons. So it forms a double covalent bond. Now, how do we know that this covalent bond is correct? We cover it over and we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And the same again on the other side. Cover this side over. 1, 2, 3, 4, 5, 6, 7, 8. It's got 8 electrons. It means both of these, by sharing 2 pairs of electrons in the middle, has got a full outer shell. You've got 2 examples there. What I want you to do now is I want you to pause the video, and you will then have a look at the examples below and see if you can have a go at these yourself by looking for the atomic number of each of these elements on the periodic table, and have a go at drawing valence electronic structure diagrams for each element that's mentioned in the number of atoms. Then see if you can draw them as covalent bonds, either single, double or triple, based on examples that we've just gone through up there. Once we've done that, we'll have a look through these together, and hopefully you'll start to see the patterns. So pause the video and start to have a go at these based on these 2 examples at the top. Right, now that you've unpaused the video, we can go through some answers. Let's have a quick drink, because talking a lot during this. Right, let's start with chlorine, okay? So, we need to draw 2 circles, and they're not the neatest, but I'll survive with that. Because we've got 2 chlorine atoms. Now, chlorine is in group 7. So if it's in group 7, it means it's got 7 electrons in its outer shell. So remember, to show the difference, we draw 1 as crosses and 1 as dots. Now, remember, if it's bonded, it's in group 7, it's above group 5, so they're both non-metals, so the bonding is covalent. So that means we have to overlap them. Now I'm going to draw some very wobbly circles, but put in the middle, Cl, Cl. Now, we've got to share electrons, and we've got to get it so that each atom has access to 8 electrons in total. So the way we should do that is we draw in our outer electrons here, and then we share the 2 in the middle. So we put the dot and the cross in the middle. Now, if I cover over this chlorine, you should see I've got 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons. It's not hydrogen, so therefore it's got a full outer shell. Same here, 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons, it's got a full outer shell. It's stable. So therefore it's bonded covalently, and it is a single covalent bond. Now, if you just scroll down a minute, because we'll come back to nitrogen in a minute, and I'll tell you why. If we go through hydrogen again and chlorine, so 2 separate circles, hydrogen, chlorine. Now let's do hydrogen as our cross. As we've done earlier, it's got 1 electron in its outer shell. Chlorine, as we already know, it's got 7. So we need to make sure that hydrogen has 2 valence electrons through sharing, and chlorine has 8 valence electrons. So overlap them. All right, sure, Cl. Now we've only got 1 electron here, so that 1 electron has to go in the middle, and there's no more that it can share. So that means it's going to be single. So it means we have to put 1 more from chlorine in, and draw in our 6 other electrons from our chlorine valence shell. And if we look at hydrogen, because it's a small atom, we should have a dot across, and it's only got 1 electron shell, so we've got 2, which means it's got a full outer shell. Excellent. Chlorine, 1, 2, 3, 4, 5, 6, 7, 8. It's got more than 1 shell, so 8 is its maximum number of valence electrons, so they've both got full outer shells, which means they're single covalent bonds. Now, to mix things up a bit, we now have 2 hydrogen atoms and 1 oxygen. So that means we have to draw 3 circles. Hydrogen, hydrogen, oxygen. As you know already, hydrogen has got 1 valence electron. And then from our previous example, you should know that oxygen has got 6. Is it in group 6? Now, because we've got 3 we still have to draw the bonds. So you'll see overlapped like this. H, H, O. Now, each of the crosses from the hydrogen go into the shared space, which means we take one electron from each of the oxygen, fill out the remaining 4. Now, how do I know that this is correct? Cover over the 2 hydrogen, count the number of oxygen electrons, and you have got 8. Fantastic. Cover over the hydrogen, the oxygen and the hydrogen, and you've got 2, which is correct for hydrogen, and same on the other side. Now, the last one I want you to focus on this side is nitrogen. Now, nitrogen, you will see, is in group 5. So, if we draw our 2 like this, do 1, 2, 3, 4, 5. Same on the other side, but dots, 2, 3. Now, nitrogen is slightly awkward, and it's an example that's worth remembering because nitrogen is a triple covalently bonded molecule, which means it shares 3 pairs. So if you know what 3 pairs are, that means 6 electrons go in the middle. 3 from the crosses, 3 from the dots, which if we've got 5 here means we've got 2 remaining. And if we've got 5 here, it means we've got 2 remaining. Now, how do we know that this is correct? Cover over 1 nitrogen and count the number of electrons that this atom has access to. 1, 2, 3, 4, 5, 6, 7, 8, including the 3 dots. 8 electrons, 8 valence electrons. It's correct. Same on the other side. 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons. It's correct. So that is why that one is one that's worth remembering as being triple. And it's just an awkward little example that is often thrown in to try and confuse you. Right, we finished on page 6, so I'll come to the last couple of pages. Nitrogen, hydrogen, carbon and hydrogen atoms. Now, again, this is just confusing, there to confuse you slightly because it's thrown in even more atoms. So you've got 4 here and you've got 5 here. So if we draw them separately here, we've got 1, 2, 3. We'll make those our hydrogen. Make those all crosses. And if we then pop in on nitrogen, make this dots. And if we do the same on our carbon and our hydrogen, 1, 2, 3, 4. 1, 2, 3, 4. And then we do our carbon. Carbon is in group 4. So we need 4 valence electrons. And you might already start seeing the pattern here, in that the hydrogen have got to share an electron each from the nitrogen atom to get a full outer shell. So you might see actually where we might start to draw these bonds. And the same applies for the hydrogen and the carbon. They've each got to share 1 electron from the carbon. So it almost shows you where you actually need to draw the bonds. So our final molecules for these covalently bonded molecules of ammonia and methane should look like this. Nitrogen, 1, 2, 3. Doesn't matter that I've done it the other way. You see our nitrogen electrons have gone in, 5 dots, and then our hydrogen electrons have gone in as our 3 crosses. And you'll see each hydrogen atom has 2 valence electrons, and the nitrogen atom, if you cover it over, total, if you count them up, has got 8. And then if you look at our carbon, the big carbon in the middle, do 1, 2, 3, 4, add them in. And as we said a minute ago, each of the hydrogen needs to share 1 of the carbon electrons. So therefore, they all have a single pair in each. And if you covered over all four, you'd see that the carbon has got 8 electrons in total, and the hydrogen have got 2 each, which means they've got full outer shells. Now, all of these examples are in here because they are common examples that often come up in exam questions about covalent bonding. So it's worth remembering these last sort of 5 or 6 examples that we've done, because these are common examples that you will see a lot of. Now, the last little bit within this lesson is something I'm going to show you to begin with, and then I'm going to leave you to have a look at yourselves, because some of these examples are used quite a bit and some of them are less so. So it's not worth worrying too much about these, but you should use this opportunity as practice. Now, if we just have a look at these first 2 here, electron shell diagrams are what we've already drawn. So we've seen this already in one of our drawings. In chlorine, we've done 2, which we know is Cl2. So we should see 2 chlorine atoms like this, one with crosses and one with dots, sharing one pair of electrons in the middle to make a covalently bonded molecule. A 2-dimensional version diagram of this. This is just the same thing. There's just no shell circles. So where these have got circles, the circles aren't drawn on, just for simplification. Now, a structural diagram shows you the element that is bonded together and then uses a line to represent the number of bonds between these. So as you know, this has got one pair of electrons that's shared, which means it's a single bond. Each line represents a covalent bond, so we just draw one line. Whereas for nitrogen, from what we did earlier, remember this is sharing 1, 2, 3 pairs of electrons, which does it make a single, double, or a triple? It makes it a triple bond. So this has 3 lines between. Have a go at hydrogen chloride, water, and then methane on the next page. And if you are struggling at all, drop your teacher an email and see if they can go through those examples with you. But these 2 examples and what we've done so far should give you enough to be able to fill in the gaps for water and hydrogen chloride. And now if we just finish the lesson on page 8 and page 9, just looking through some questions about covalent bonding and just seeing if you can have a go at them. So this will be your next point. Pause the video, have a look at the questions, see if you can do them based on the lesson content that we've done, use any extra revision resources, online resources that you want to use, and then we'll go through the answers to finish, just to see if you've grasped what it is that we've looked at. So pause the video and have a go. As you might have noted from the sound effects, that pause was there for me to have a drink. So now that you've had a go through these, let's just go through the answers to finish. So first question, state the number of atoms shared in a covalent bond. So a covalent bond implies one covalent bond. So one covalent bond is between 2 atoms, and each covalent bond, whether it's single covalent bond, 2 electrons are shared in every covalent bond. Now, explain why atoms want to complete their outer shells, their valence electrons, or their highest energy levels. All atoms are wanting to do this to become stable and unreactive. State the number of pairs in a triple bond. Triple, what does it mean? It means 3. Suggest why the non-metals needed to share electrons. Again, why are they sharing electrons? Because they want to get full outer shells. To become stable. So Write the structural formula for water. Now, if you look back at the table, remember structural formulas are the element symbols and a line to show the number of covalent bonds between each. So if you think about water, it is H2O. So it's got 2 hydrogen and 1 oxygen. Now, it's going to be 1 covalent bond between the hydrogen and the oxygen, and 1 covalent bond between the hydrogen and the oxygen. So that's your structural formula. Now, a sixth question. Explain why the oxygen needs to have a double covalent bond. So oxygen to oxygen. Why does it need a double covalent bond and not a single? So each oxygen has 6 valence electrons. So therefore they need to gain another 2 electrons to get 8 electrons in a full outer shell. Now, it gains 2 from 2 covalent bonds with another oxygen atom. So therefore, if it gains 2 from another oxygen atom, what that means is that both oxygen atoms can share 4 electrons, and then if you add that to the 4 other electrons each atom has in its outer shell, means it gets 8. Chemical formula for methane. So chemical formula implies symbols. So what is the chemical formula for methane? Methane is made of hydrogen and carbon, and it is CH4. And then on to the last few questions. Draw 4 different diagrams to show the bonding in a nitrogen molecule. I'm not going to do it again, because if you look at the table on page 7, you will see in our example 4 different diagrams for an electron shell diagram, 2-dimensional electron shell diagram, a structural diagram, and a ball and stick diagram. What's the structural formula for ammonia? Ammonia is NH3, and it is single covalent bonds, as we've done in our previous examples. So it should look like this. Suggest why the nitrogen molecule has a higher boiling point than hydrogen. Think about the amount of energy required to break bonds. N to N is a triple covalent bond. And triple covalent bond needs more energy to be broken. Write a chemical formula for hydrogen chloride. Symbols, HCl. Write an alternative name for shell. So you might have orbit, you might have energy levels. And then name the group of elements that are unreactive because they have a full outer shell of 8 electrons. It is on noble gases. So we've covered the main content there on covalent bonding. So if you've finished there, great, but there is also the extension activity at the bottom. So if you want to pause the video and have a go at that, we'll then finish just explaining the extension activity. So pause, have a go at that, and then we'll go through the answer to finish. Right, I should have paused it. So if you've unpaused, it says explain the carbon dioxide molecule needs double covalent bonds. Hint, you'll need to look at the position of oxygen, carbon in the periodic table to find out the number of electrons in its outer shell. So we know already from our examples, oxygen has 6 valence electrons, doesn't it? So if we think about what we've got 1 and 2, and then 3, 4, 5, 6 carbon. We know it's got 4, 2, 3, 4, and then same again for oxygen. 1, 2, 3, 4, 5, 6. So if you look at this and think, right, this has got to get and share 4 additional electrons to get a fallout shell. These have got to share 2 additional electrons to get a fallout shell. So if we draw it covalently bonded, we've got 3 atoms. So we draw carbon in the middle, draw oxygen on one side, try and make a big enough overlap, oxygen on the other side. So this has got to get 2 additional electrons, hasn't it, to get fallout shell? So it's going to need to be double because it's going to get 2 additional electrons. So it's going to share 2 with carbon, isn't it? And then these 2 are going to be shared with carbon, aren't they? So we're left with 4. 1, 2, 3, 4. The same's going to apply on the other side. 1, 2, 3, 4. So how do we know it works? Cover over these 2. 4 plus 4 gives you 8. And then same.
4 plus 4 is 8.
And that's Siri telling me that 4 plus 4 is 8. I didn't ask him, but he can shut up. And then on the other side, 4 and 4 is 8. And then you are left with, in the middle, 2 sets of 4, which again gives you 8, which means each of these has got fallout shells, which means they are stable. So it's a stable atom of CO2, which, remember, 2 shared pairs is a double covalent bond. Well done, folks.